All right, so we're back at ellipses. We had previously looked at one in a nice vertical position. Now let's go from giving some information about the vertices to actually get to the equation. So I find the standard equation of the ellipse with foci at 0, 1, plus or minus 1, and the vertices at 0, plus or minus 3. So I know that we're talking about my vertices being at plus or minus 3. So I know that this, okay, is going to be my major axis. Okay. If I look over here, what other information I'm given, I know that C is equal to 1, which means that C squared is equal to 1. So by manipulating this equation, the original equation, C squared equals A squared minus B squared, and I'm solving for B squared because that's what I have, or what I need. I need B squared, so I'm going to take and manipulate this equation into B squared equals A squared minus C squared. A squared we know, because we know what our major axis is. We know it's 3, therefore 3 squared is 9. We know what our C squared is, that's 1. So I get 9 minus 1, and there's my 8. This is my B squared. So then I can take my B squared, just come down here and plug it underneath the X squared, put my 9 as my major axis under my Y squared, leaving the 1 where it is because that's what we used as our equation. We worked backwards from that, so we know it's equal to 1. And there's my equation of an ellipse in standard equation of the ellipse with foci at 0, plus or minus 1, and the vertices at 0, plus or minus 3. Okay? So that's fairly easy to work backwards from. In fact, it's probably easier to work backwards from this problem than it is to work forward from the standard equation, because if we sat here and we looked at this standard equation over here, the first thing we see is that 8 is not very easily square rootable. That just not as easy as we would like it to be. We wind up getting 2 root 2, and we're not as comfortable dealing with. Okay? So reflective property of an ellipse. Something about parabolas and ellipses that we use in real life is the reflective property. The fact that they do have foci. They have a focal point. Those of us who have to wear corrective lenses, okay, are well aware of that fact. Like the parabola, the ellipse does have that reflective property. If it's rotated about the x-axis, the ellipsoid, which is the three-dimensional figure created by having an ellipse being rotated, okay, is formed, which resembles the shell of an egg. Or more importantly, if I split it in half and I looked at this, a lot of times this used to be how they made headlights on cars. They used ellipses. They also used parabolics, and we'll get into that when we talked about parabolas. If a light source is placed in the focus, then every beam of light emanating from the light source, regardless of its direction that it's shown, is reflected at the surface of an ellipsoid toward the focus F2. So if I start here at F1, no matter where I throw this beam of light, as long as we're talking about inside the ellipsoid, it will be reflected and directed toward F2. No matter where, even if I put it off the back wall, it'll come right there. Because that is exactly how it's designed. It's designed such that any reflective property, no matter where, that surface will be facing the opposite foci, regardless of what foci I choose. standard equation for ellipse centered at h comma k. So now we're talking about not so Fisher-Price problems. We're talking about taking the ellipse and moving it off of our center. We're no longer at origin. We're no longer at 0, 0. An ellipse with center h comma k and a horizontal major axis. So we're talking about our ellipse that looks like this. Satisfies the following equation. Again, we're still going to hold true that a is greater than b is greater than 0. So a is still going to be our distance of our major axis. C squared is still going to be the same with a squared minus b squared, and c, of course, is going to be greater than or equal to 0. Most of the time, not equal to 0. But we'll get into that. So here it is. It looks relatively the same because my A, being the larger point, is on my horizontal. B, being the smaller one in this case, is on my vertical. We still have our buddy 1 hanging out here. The only thing we have done is something that we're relatively familiar with, our friends h comma k, and all they have done is shifted our equation. Now, notice it's minus and minus, so again, if I want to move it in the negative direction, I have to put plus, because that's minus minus. Okay? Much similar, and you've all seen this before, this should look familiar to you, because when you dealt with quadratics, you saw the h and k do that shift for you. Now k shifted what? K shifted in the vertical direction. K again is going to shift in the vertical direction. H shifted in the horizontal direction. H again is going to shift in the horizontal direction because it is down here attached to the x value, which means we're dealing with the x-axis or the horizontal direction of this ellipse. So none of this should be too confusing or too new to you because we are talking about values that we have seen before. So again, our h is going to move us left and right. Our k is going to move us up and down. But everything else from our previous ellipse equations are going to remain the same. Okay. Now here it is with a standard centered around h comma k, just a given point, and a vertical major axis. So now we're looking at the equation of an ellipse in this direction. Here's my x, here's my y and x values. So we see now that a, which is always the larger, because we are still holding true that a is larger than b and b is larger than 0, a is now representative or attached to the y direction. B is attached to the x or horizontal direction. H and k have not moved because h is still going to be our vertical shift. K is going to be our horizontal shift. So we don't swap those around. We leave them alone because we're comfortable with that. We like that same nomenclature. We want to see that consistency. So here we will begin with a relatively Fisher-Price problem. Notice again that we use some relatively Fisher-Price numbers that we know we can easily find the square root of because that's not what we're focusing on. We want to focus on where is our ellipse moved to? How has it moved around in our coordinate plane? So we label the vertices and foci. The first thing we do is we find the vertical major axis centered at -2, 2. So we know that it's centered on -2. See this plus? And we had a minus, -2. So -2, 2 is our centering. So now we're going to have an ellipse that's centered at -2, 2, somewhere around there. We know that a squared is equal to 25. A is our major axis. So we know that our ellipse is going to look something like an elongation with the elongation in the vertical direction. We know that b squared is 16, and we know that c squared again is 9. Thus, a is 5, b is 4, and c is 3. So let's take a look at how this bad boy looks. We see that we have a centering, okay, a centering around negative 2, comma 2. So somewhere in here. Okay. The vertices, though, now we can't just use 5 and 5 because we're not centered there, but they are 5 units above and below the center. So if I'm at negative 2, comma 2, and I go 5 units up, I'm just adding to the y value, so 2 plus 5 is 7. 2 minus 5 is negative 3. Okay? I can get my horizontal ones relatively easy by adding 3 and subtracting 3. Adding 3, subtracting 3. Okay? I can also find my foci. They're 3 units above and below. So if I have 3 units above negative 2, comma 2, that gets me to 5. Let me change color so I don't get this too confusing. That gives me 5 and negative 1 for this spot right there. And thus we have our graph. We do a nice smooth curve between those points, and we have the best graph we can get. So now, let's write this long equation in the standard form for an ellipse centered at h, comma k. Identify the center and the vertices. So we know that we need to get 1 somehow. I'm not sure how we're going to get there yet, but we know that we're going to need to get there. So the first thing I need to do is get all the terms together, and we see that we have these relative terms together. The y's and the x's are together. Let's take the 61 to the opposite side. Okay? So that should be plus 61. Okay? And here, we pull the 4 out of this. We get x squared minus 4x plus, and let's complete the square. So we take this, remember b divided by 2 squared. So negative 4 divided by 2 is negative 2. Squared is 4. Same thing here. We take 6. We divide it by 2, which is 3 squared, which is 9. So I come down here and I put 9 in. Now I've completed the square, but I've added 16 and 81 to that side, so we have to add 16 and 81 to the other side. Okay. I continue with breaking this down. I know that this is now a perfect square, so I write it like this. I know this is a perfect square, so I write it like this. I simplify, I get 36. You know what? Let me go back for a moment. I do apologize. I think there was an error in my original problem. This should have been plus, because that is supposed to be a negative. So we get 36. Our problem works out a little better that way. So we're going to say that this is a negative, so that this does become 36. Again, Fisher-Price problem. So now we have a perfect square. We take 4, we divide both sides by 36 because we know that we need to get 1. So now I have this divided by 36 and this divided by 36. I break these fractions down. I get 1/9 and 1/4. I put them down at the bottom. I know my center. Okay? I know my center, and I have a typo here. I know my center is at negative 2, but that is a negative 2, because remember it's x minus h, so it's actually just the h value, so it's 2. And here I have y plus 3, So I can make that equal to y minus a negative 3. Take that negative 3 and come on down here. It's like the Price is Right. Come on down! And there I have my equation. This ends the second section on ellipses.